Good afternoon, everyone. Um, I'm thankful for this time. My name is Mauro Vargas. I am the director of the Institute of Ocean Institute with the Physics Department of the National University, and I also coordinate the National Service of Marine Exploration. Today we will be speaking about smart monitoring of coastal waters and oceans, tools for high technology for marine exploration. This presentation is also important because we also wish to celebrate the Ocean International Day, and we also have a special someone who is invited, a special invite, who will be sharing with us near the end of the presentation. Okay, so is there an issue that maybe, why can't we see it on the screen? Oh, okay, now we can. All right. Now, why is it important to study the ocean and the coast? The ocean regulates weather, the weather patterns of Earth. It dissipates heat, and it also gets rid of CO2, carbon oxide, through the thermal haline circulation. The red are the superficial ones, and the blue is the deep ones. And in heat-wise, due to the tides, the heat goes to the poles and vice versa, and that helps to regulate climate and weather in general for the entire globe. Also, it is a source of oxygen. We know that the plankton produces a lot of oxygen, even more than the forest. It's the lung of the planet, basically. And it also provides work and food. It provides an income for many people along the coast of our country. It also works as a transport of goods and people. Ports all over the world are a source for the economy in every country. And even besides this, how do we study this? How do we study this? How do we use the ocean? And that's what we wish to share with you today. The equipment that the people who study the ocean use. They're instruments of high technology in oceanography and physics. Physical oceanography. So we have an acoustic Doppler current profiler, which has an acronym of ADCP. It measures the velocity and the direction of currents in water using an effect in physics that we call the Doppler effect. The ADCP transmits sounds through impulses, and those beeps frequency is shorter. So that change in the frequency is what the apparatus does. It utilizes that and it transforms it of the frequency. And then we also have other sources. And then there are other ways as well, such as a floating, like a flotation device. This is an example of an apparatus that we have in the lab on ADCP. You can see it here. This blue one, it's painted with anti-rust paint, and so we put that in the ground of the ocean, and we leave that there anchored, sometimes months, or sometimes even years. We leave that at the sea bottom, and so then we can use that to make statistics. And we also have pressure sensors and some sensors, maybe the height of the wave, etc. We can also use the same apparatus in a similar way from a ship in movement. Measure all of that. Turbidity, all of that. We can use anchor that, and then after several months, you can see how it's covered with marine flora. And another way we can use that is as a profiler. With a ship, we can set up a parameter, and we use that as a profiler, and we use kind of a column there, and that's kind of what we can see on this end. This is a typical profiler that's used from a ship. There are some smaller ones that are more compact, that maybe are only temperature, pressure, and salinity. But there are also other types. You can even see it from the ship. There are other equipment, many more. We can also set up different parameters, sensors at different levels, and we'll leave them there for a long time so we can provide analysis of temperature, different changes. And another apparatus that's very important for us oceanographers is an oceanograph of radar and a pressure sensor. We use electromagnetic waves, a tidal gauge, and to confirm those lectures, we also introduce or we place pressure sensors with several meters above water, so we can also confirm the levels in the water. We obviously need several ships for this logistic, different boats. We also use buoys. We can see this yellow one with solar panels, And really, we this is a basic one, but we can put some other ones that can carry even more equipment. And this is a simple one. This is has different temperature sensors and different levels, and it can also measure the wind and the surf. And what's great is that it feeds off of solar panels, solar energy. So that's great because we can move that around. This is an example of one of our colleagues. They installed one in the Caribbean. That's one that's like the one that we have on the table there. And with that, we can measure several variables. Another tool that's a great use are the models, the computer numeric models. And in the lab, we use models to understand the physical phenomenon that governs several elements. And what's a model is that we can simulate nature. So we can include the different strengths once at a time to see how the model would react. And that simulates nature. So we can simulate levels of water, flow rates, temperature, salinity, density, among others. And when we add one of the constitutions of tides, and you can't completely understand the currents, we could add the wind velocity or other factors until it's is similar to the results, so we can understand what's most influential in those results. So that includes different modules for simulation, hydrodynamic, water quality. Another quick example that we are simulating in the Nicoya Gulf, we have here a non-structured grid. And we can include the river flow, river discharge. We can also include salinity in open borders, harmonic constitutions that constitute the harmony, and also the modeled wind. This is results, a quick result for, we can kind of see these are some points of observation. We have one in Punta Arenas, and you can see them there, and this shows the level of water, and you can even see it. So if you understand it, you see the observations, and what's red is the model. So you can see from the rainy season to the dry season, it's almost exactly the same, which means that the model is doing a great job. It's doing a great simulation. And when the model, we have that capacity to reproduce something that already happened, we can, in the future, simulate any type of prognostics for weather, so we can, that's an operational instrument. If there were a storm in the middle of the ocean, and maybe there's a high tide and an extreme in a certain place, with an operational model, if we simulate that point, that can help in decision making. This is also an animation of simulation of salinity. And what we see here in blue is sweet water, or almost sweet, almost near zero. And then the red is 33, which is kind of like yellow, and that's kind of like ocean water. And so we can see the simulation there in 2021, where we try to describe and illustrate the tide. And we can see how the most important river, which is Tempisque, how the sweet water meets with the salt water, and what's the preference as to where it moves. So we can see that it's right between that island there and the continent, which is called Isla China, China Island. These types of things are of great use for planification, projects, for example, for marine culture. And I will finish here. I will give the floor to a colleague of mine from the lab, Alexander Kisoa. He's a marine biologist, and he also has a master's in coast biology, and he's here to show us some results of the project of Nicoya Gulf and shows us how some of these equipments are used. Good afternoon. How Mauro said, I will speak about some data from the Nicoya Gulf. That's the estuary, the largest estuary that we have here in Costa Rica. So we started with measurements in the Gulf, along with the School of Biological Sciences. We had an interest in knowing how the oceanographic variables affects the ocean and different fish farms in the Nicoya Gulf. So those that are familiarized with the Gulf, that's in the Central Pacific portion of Costa Rica. And the data that I will show you are from Punta Arenas, specifically from an anchorage that's that's facing southwest from the dock. So the first data that I will show you correspond to data from ADCP. What was anchored was the blue one, the last one on the table. As Mauro mentioned, this apparatus measures currents, and we can see that here represented with colors. The blue is the water entering the system, and the red is water leaving the system, and this is the pressure that is represented here with the black line. So it'll show us the how the depth changes along a period of time, and if we close up, we will see a portion of this data, and we will see the variation of the water with variation of currents. So when it's higher, it's because there's a current entering the system, and when it gets lowered, it's because it's leaving the system, the instrument. So we proceeded with making a harmonic analysis. How much is adjusted the marine to the variations, and we can see that they are adjusted quite well. The graph here on top, we see the variations of water and what's in black, and then what's in red. I hope you can see it. Maybe it's a bit difficult to see. It's the harmonic model, and according to the adjustment, it's almost a 94% from the model to the observation.
We then did the same procedure with the average current vertically, and we see an adjustment of 92% almost on the model of the observations. So what this means is that currents or tides, the relationship between them and the level of water in this area in the Nicoya Gulf, there's variations of hours and days. These are being explained by the tides. Then we proceeded to remove these variations of days and hours, and we kept the variations of more than 2 days. We can see data related to currents and tides, and there is an intensification of the tides together with the live tides. So what it says that in this point in Nicoya Gulf, current and tides are dominated by these tides in scales of hours, days, and even weeks. These variations seem to influence the variables that are taken with CTED. So we have a graph with temperature, level of water, salinity in black. And these variations that we can see, small ones here, are related and correlated with the tide. In the same way, the extra sensors that the CTED has of chlorophyll, the data that it takes, it's also influenced by the tides. Now I'm going to present to you briefly some data from an ADCP movement. These data were taken very close by to where the method was located before. But we have a transversal resolution, which is better spatial resolution, and we got to profound points and spots. What we could see and observe in the immediate currents is that they are also influenced by tides. So here, for example, we started measurements at 4 a.m. We can see a current coming in the system. So water was still going up. At 5 a.m. it starts changing, so we have water coming out in red and water coming in blue. And as the tide cycle goes by, we get an increase in the exit of the water until the tide goes down. So, of course, to summarize, tides are very important in the Nicoya Gulf. And what we must try to see more is the effect of other factors that could be important in these systems, like, for example, wind, and also the density gradients provoked by the discharge of the rivers in the Nicoya Gulf.
Gracias, Tizón. Continuamos con el profesor Juan Pablo Salazar.
We continue with Juan Pablo Salazar, the professor. He's going to talk about another application that there is in Santa Elena. He's a meteorologist, and he works in with his masters in the coast. He's going to talk about another bay, which is further north. Go ahead, Juan Pablo. He is from the lab coordinator and the coastal management as well in the physics department. Thank you, Mauro. So first of all, good afternoon. I'm going to talk a little about by Santa Elena, the bay, which is another area that we've been working on since 2018. We were invited by a colleague that is not here, and they were doing a thesis, and he said, why don't you go do some measurements? And starting on that point, we started doing some measurements in Bahia. In Santa Elena, we have several findings. First, we are in the North Pacific in Costa Rica, just for location. We are focusing on the limit area between Costa Rica and Nicaragua in the border. We are here in the Santa Elena Gulf, and within the Gulf, we are in the Santa Elena Bay. We're going to show the temperature data that Mauro described, and we obtained this information from the department that has helped us with these measurements, and this is the equipment that we're using, that we're going to present. Here we have the method that we actually dropped down there with some kind of tie, and the sensor was placed in different profundities. So water is not that cold, we actually remove the average. The goal of removing the average to this data is see when it gets warmer and colder. The purple color indicates cold, and we are seeing 5 series of cooling that we are indicating with these yellow circles, and then we can see that water gets heated again, and it repeats its cycle while cooling. So using a mathematical tool, we're trying to see what's happening, and this mathematical tool, what it indicates its modes, and it tries to explain from 1 to 100 how much it explains. The first mode that we have in this mathematical tool is giving us an 86%, and we can see that the 5 events of cooling are kept and maintained. So our task now was try to correlating why and what other variable makes this cooling process happen. So we did a correlation together with wind. This correlation of wind gave us 0.55 with along 21 hours. So that means that we have to maintain strong wind condition around the whole day so that this cooling process can be happening in the bay. So the theory that we have is that in Central America there are 3 mountain areas that go by. For example, the mountain between Papagayo and San Juan, the lake. Wind gets by in a very strong motion, and it forms this kind of this wind turbine that is very strong, that it would be associated with the cooling process. So what do we have in this area? In the Gulf, we're going to have these winds that are strong, that are going to produce this movement with this red line that we see here, and it's making the water go outside. We can see that whenever we have some kind of soup that is very warm, and you start, then you start blowing at it so that it can cool down, and this is the effect that happens on Earth because the movement of the mass of water is towards outside. Something else that would not be produced is that we have a level of the ocean like this, and thanks to this movement of mass of water towards outside, we would have an inclination. Outside of the coast, we're going to have an accumulation of water mass. And there's also, because of conservation of mass, since we're moving more water outward, it is substituted with mass that is coming from deeper. So this water is colder and rich in nutrients. We have to be clear that this is happening in the Gulf. So it is so big that also the bay starts cooling. So since wind relaxes, I forgot mentioning that these winds are papagayos. Then the gradient of pressure disappears. So this mass of water that we had outside starts coming back, and we go back to normality. So all that water comes immediately, and we're going to have this circulation that we are indicating in red. So it comes in, turns around, and it goes around the bay. That was the theory that we had. And for that, we used the equipment that today has a yellow hat to see if that would happen. So we left this device in the seabed, and we are going to have a flow outward. This is what we think. This data that I'm showing, we actually removed the effects of the tides. So what we're seeing in red are positive values, which is outgoing, and what is in blue is incoming. We can see that predominantly we have the red ones. So I am indicating an event here that, if you remember the figure from before, it matches more or less after the first cooling period. And the following ones are the following flows that we saw. So after these strong wind events, whenever there's a cooling, we're seeing this circulation with the ASP within the bay. In this image here, we try to summarize everything that I'm trying to express here. And here, we also have information in this yellow point, which is related to the equipment that we have on the table. So on the graph above, we are looking at the temperature, the anomaly. And in these lines, I hope that you all can see, these are the cooling events. And then after the cooling events, we are seeing at the average speed of the column of water, and in the yellow spot we can see how water came in, and that's why it's going on the contrary motion, and the black one is here and we're seeing water there as well. So that matches with what we are trying to explain. This equipment has a capacity with the sensor that we have here at the top that we can barely see. We can measure pressure with how much water there is on top of it. And we obtain this graph. What you see in black is what the equipment gave me, and what is red is a prediction and forecast based on the observations. The statistics gave us very exact numbers. With this, ideally we could leave it more time down there so that we can get to 100% with that anchor. So we're going to work with data from Espinosa that we've been working with. We have in different sectors, and we have observed the red snapper fish as well. And we're going to see if there's some correlation with the tide. So using another statistic tool, in this axis we have time, and in this x-axis we're going to have density of energy. Density of energy, what we can see in colors. In red, energy is higher, blue is lower. And if you're seeing it marked, it means that there's statistical symbolism. The first thing we want to highlight here is this band around 24 hours. And it has some jumps there. Those jumps are live tides. And the other band that we're seeing is the 12-hour band. The 12-hour matches the tide that predominates in Santa Elena Bay, which is a tide that repeats every 12 hours. So it fills and then it empties, approximately 12 hours with 42 minutes. So this provides shelter for smaller species of fish, protecting them from predators, and it provides the possibility of more variation. Here, what I'm presenting is a low tide close to the receivers. And when the tide goes up, which is what we're seeing in green, it flooded several areas, and these areas is where we have mangroves and wetlands. So red snapper can access the mangrove. This is important because we're finding shelter and food. So the red snapper does some kind of dance. They understand the tides. We don't have to explain, of course. What's important is that Santa Elena Bay since 2018 is marine protected area. That means that human activity is controlled. And why is this important? Because it's a shelter area for the red snapper. It provides shelter, food, and so it's like a sanctuary for them, to call it some way. And with this, just to finish off, it says there that the red snapper can dance with the tides close to the mangrove, depending on their size and species, because of shelter and food. So to finish off, we saw a process, a meteorological process that we associated to a sociographical process, which is combined with the marine and oceanic aspects of biology. Here it is important to highlight that because it's very few studies and research done in the coasts in Costa Rica that where they try to do this. Why don't we do it? Well, the lack of alliances and budget. Equipments to do measurements close to the coast are expensive. Maru just talked about some kit that would be amazing to have, but, well, we need budget for that. So we can keep that idea. Thank you, Pablo. As I change the presentation for the following speaker. While Mauro gets ready, I want to thank the students. Many of the processes has been thanks to them, so thank you for all your support that you've provided in the Congress. Now, next one is Dr. Vincent Thaillandier. Dr. Thaillandier belongs to the Villefranche lab, the Villefranche lab, and it is associated to the National French Center for Scientific Investigation and Sorbonne University in Paris. He's a physician with particular interest in the oceanic circulation and his biochemical responses using field studies and observation systems globally, like the Project Argo, satellite, and altimetry. He was part of Sally Ride that took off from Punta Arenas 2021, and he had the opportunity to do sampling in the tropical Occidental oceanic. He also collaborated with National University. Thank you for visiting. He's going to do a big effort to speak Spanish in the talk, so he speaks very good Spanish. Just in case, you can change to English.
Good morning. Thank you for being here. Also, thank you to Dr. Vargas for his presentation, his introduction as well. Today, the exploration of the oceans has its base on in the development for our institution, our French institution, a submarine that is called the Profiler Floater. And we will show the different components and how it works. It's a device. Okay. It's a submarine robot to observe the interior of the ocean. It moves passively with the currents, and it has the capacity to move actively between between being shallow to going more in depth. And it's programmed to repeat a cycle that is illustrated here.
descenso hasta
It
la
descends
profundidad que se llama de deriva,
to the
posiblemente a 1000 metros,
to this
se
portion
lleva aquí
of
hasta
the
el mayor
drift,
centro
which
de
is
la
kind
Tierra,
of the middle. Here it spends half of its time in
usualmente 1000
this,
metros, y después
usually
tiene esta
1,000 meters,
de ascenso,
and that's the depth. And then it can also access
donde este ascenso hay la activación de los
more
sensores para
depths
medir
and
las
activate the
variables
sensors
térmicas.
to measure different variables. And then the last phase is the transmission phase to Earth, to land.
En promedio,
In average,
este ciclo
it repeats this cycle 250 times,
que nos presenta
which makes it have a profile for 10 days during 5 years of operation.
se debe a su
And this is due to its low
la ubicación
consumption of energy. I will show you the battery here.
gran parte de la
A great portion of the components
están en el carbón
are in
esta parte
the middle of this instrument, this yellow portion here
de los componentes.
of the components.
Tiene mucha batería ahí, pero así puede
And it can operate during many years.
puede también
Why can it also last for many years? It's because it has a hydraulic motor that a hydraulic system that activates its movements and its slow movements. And how does that work? I will show you two parts.
esta vejiga interna
This inner portion and then
en una parte que se llama
an inner
externa.
bubble that's kind of external,
Es constante.
and it's constant. So only the volume can be modulated between a oil reserve that will be transferred
La vejiga interna
from this inner part to the external portion.
este cambio de volumen
And then this volume here
la fuerza de
will make it move the density and velocity. When the
la reserva de aceite se reparte
when it's floating, the oil will be spread out between both. That way that the Archimedes force compensates exactly the weight of the floating device. And when the oil is toward the exterior,
en la vejiga externa.
in the external bubble there, the volume increments, and then the pushing force for Archimedes also increases, so it gets higher. And when the valve goes in and when the oil goes into the floating device, the volume decreases, and then the pushing force, the force also decreases.
Adquisición de medidas.
Here we have the measurements,
La adquisición de medidas
the measurements acquisition. And it's this component here.
tablero electrónico
It's an electronic graph,
es un tablero de control electrónico.
an electronic control
Tienen durante el ascenso
board,
permiten de crear un perfil
and
de las variables
that
sociales,
allows
como las variaciones
different variables, electronic variables.
que se ven en
And the ones you can see here in this figure, the acquisition of measurements is thanks to this board, this control board, which allows to obtain each data with a predefined definition. For example, the CTD can obtain measurements every second, which equivalates to a profile of 10 centimeters. For certain other apparatuses that need more energy, this one can last for 1 minute and therefore is equal to more data. And from our lab in France, we can also show the algorithm for this board, and also some heavy data such as images, sounds, and we can process this in a lighter manner. And it's on that board where the data is registered in a unique archive that will be provided the next time it reaches the surface. As we've seen in the navigation cycle, the floating device connects with a satellite network that's called the Iridio network, and it only connects when it's in the surface. And this phase only lasts 20 minutes, when it should send its GPS location and the data obtained in the 6 previous hours. And that's here in this antenna, that's the GPS and the satellite communication. So it's kind of limited, 12 kilobytes per minute. So then the data transmitted is around some dozens of kilobytes. It's small. This data are communicated to land and saved in its database and then placed for disposition for everyone who might obtain it, and operation services for alerts and operations, and also for quality control and the scientific investigation. And this satellite communication also allows to receive orders that a pilot has previously prepared. So then that is how we could, for example, change the performance, change the depth if it should move toward the coast, or also kind of set it to a drift mode in the surface for recovery. This floating device is equipped with a 7D, that's right here. It's a miniature next to this CTD, but that's the most common version and the easiest of the floating device. And 15 years ago, we equipped this with the application biogeochemical. And in the program that I lead, we also lead different analyses as nutrients, oxygen, biomass, or all type of measurements that are accessible with sensors specifically that are added on to the computer here or there. And we also study the destiny of the phytoplatonic area, the sedimentation, and yes, inside It's a European project called Refine, and we've annexed to the floating device to estimate the vertical flow of particles, and then also a camera for the detection of the phytoplatonic floor. And then we also have some applications for different systems, geoplatonic systems, and some months ago also some acoustic sensors. And that's within the framework of the project Argo Dome. And that was also presented here in this Congress with the Physics Department of the National University as well. And there is a poster elsewhere for more details on the project. I also wanted to show an application. Where is it? Let me look for it. In the flotation devices, an example is a detection of marine life through fluorescence. The biomass of phytoplatonic floor, the floor meter, thanks to the light and the process of photosynthesis, and the mass of the phytoplankton, and the different size as well, which is less than one, very small meters for measurements for the antenna. And then the measurements for the water also characterizes these microcosmic particles that are suspended in water. And thanks to this fluorescence phenomenon, we can distinguish the phytoplankton from other particles, organic, mineral, of the same size. When they are illuminated with a blue light, the different pigments that allow the cells for photoplankton allows the excitation of that, and it emits a light of less energy in the red range. And that's how we can detect marine life through this, with this measurement principle to quantify the quantity of chlorophyll also related to the fluorescence emission. And all of this formation, we can see that in all of the oceans here in this illustration, and that's called the World System for the Observation of Oceans, the Argo network, and that's set up for 4,000 active floating devices. And that would be a component for a world system of observation of oceans. And every year, they project 200,000 profiles each year, and all of that data is in free access. And we have 550 profiles each day are used in real time with different measurement systems. The Argo network is one of the main instruments for the monitoring of climate change. It monitors oceans for the mitigation, and it also absorbs an excess of heat and also the CO2. The data collected within this observation system have allowed
han permitido um, de confirmar
to confirm
calentamiento
the
de los
warming
océanos
of
durante
the
los
oceans
últimos 20 años.
during the
Y
last
esto
20
con una
years.
precisión
And this has a precision,
sin precedentes.
an unprecedented precision,
Modelos numéricos usan
very
técnicas
accurate,
algo,
and
por ese
many
lado,
instruments
al-
use
al-
these
por ese
Argo
lado,
data,
este calentamiento
and that's related
de
to
2 grados
the
con las
warming of
emisiones
almost 2
de
degrees
oxígeno,
emitted
dióxido de carbono
through the
emitido por las actividades humanas. Midiendo la
to
emisión
carbon dioxide
planctónicas,
due to
los
human
flotadores
activities.
de Argo son útiles
So
para
they are also
cuantificar
very
la
useful
emisión
to
de
quantify
carbono orgánico
the emission
en
of
los
CO2
océanos.
in the
Su
oceans
secuestración en las profundidades,
and
así calificando su
the way it also
orden
remains in the
estimativa.
depths of the ocean.
Por último,
Lastly,
otras aplicaciones de los flotadores
other
Argo
applications
en el apoyo de
for
sistemas
the
de
Argo
información
network
ambiental
is the
una
support
variedad
of
de
data
servicios
information
operacionales.
and operations.
Argo mejora
Argo
los,
improves
previsiones
meteorological
hidrológicas y
provisions, and for the ocean, Argo betters the systems for alerts for external phenomena such as hurricanes, cyclones, storms. Argo is useful for the management of ecosystems such as fishing, eutrophication, and deoxygenation. Oxidization. So thank you. Thank you for your time. Thank you, Valsan. That's an excellent presentation. We will now move forward with questions. If anyone has an observation or a question for any of the presenters, especially our guest, which is an expert in Argo, if anyone has a question online. Okay, I will give you the microphone.
The instruments and tools that you're using incorporate a camera, right? To observe the object. So what size of organisms can you determine with the system of images?
El rango de tamaño es de cientos micrómetros hacia
I believe he's at 200 micrometers, 100 millimeters, from 100 micrometers to 100 millimeters. So it does the whole range. And you can also see the aggregate and the particles, organic particles, to that aggregate to sediment. And you can see the microplastic fibers, molecules, whatever we actually pick up with a net. I don't know if you said it before, but what type of receptor do you use to capture the fluorescence of the plankton in general? Type of receptor, the technology is same as the sensors sensors that we have here. They are the same size, and they are on the top of the floating material. The sensor it does some kind of pulsating light impulses in blue, and there's another window that picks up the light in the lead that is relative to the fluorescence or the blossoming. That's how you can quantify chlorophyll based on the greater pigment that is part of the photosynthesis. I would like to comment on the last picture where it shows temperature, the surface temperature. Maybe we can comment there how important it is to use models, and maybe you can comment a little about the importance of the use of the model. So the first floaters and the beginning of the Argo network is for about 20 years, 2000s. So that means everything here that we can observe has the comparison of the observation of in situ that are measured for these floaters. That is something that we rebuilt with all the observations in red. And also these observations are used to calibrate models and medical simulations that, as you said, of doing scenarios, if there is a scenario and there's no warming in the atmosphere and another one with the warming of the atmosphere, and these are seen in this envelope. These are simulations are here, so in that way you can see that the warming of the oceans is very well relative, is not natural, rather it is with a component of the effects of human activity. Exactly. So if we only include these greenhouse gases, we the model is similar to the observation. That is what he's saying. So how do you control humidity within the floater? If there is any difference in the pressure by some dissecting aspect, maybe there is a internal pressure sensor that tells you if pressure changes or not. At the beginning, the pressure inside is low, so it has to lower the pressure inside the box, and when the pressure goes up, that means that there's a problem. But with humidity, maybe it's not necessary. Maybe with just pressure, you can see the livelihood of this floater for pressure. If there's humidity, maybe it's going to affect other components. But yes, inside, they add this salt in these parts. Any other question? And the floaters that you're putting out there in the ocean, have you been able to try the EBD arm? Yes, this model is a model that has conductivity measurement with resistance cell. It measures tension inside. Everything here is a tube. And there's another method of measuring that by induction. And the one that you're mentioning, the CTD idea, uses this principle. The advantage is that there's no flow that is active for one tip or pump, and in that way it consumes less energy. And it is less exposed to the biofilm that we saw in your picture. So those are two advantages of having this technology. And about 2 years ago, that there are more and more floating devices with this. There's companies that are fighting a lot to have the market on sales on this. My question was related, what are the main challenges that you face in the implementation of this type of equipment and tools, and how you can face them? Challenges in general, whatever you think is important. General challenges that you face while placing these devices in the ocean. Yes, this is deployed in the open ocean. When is it used? There are applications to it, and teams that want to use it for the coasts. Here there are more problems because there's a higher probability that the floater is gonna go to the beach, since it is in the coast, or it will find and crash against other ships or boats. But in as a whole, global probability of the network, it is more about battery than that can terminate the operation more than a problem. There could be a deficit on sensors that can affect, and for biochemical applications, we're looking at how sensors use optics. They have to be very clean, and you can see these measures because there is some kind of deposit of a film that is created, but the majority of the time this is at 1,000 meters, and normally it's not always clean. Sensor isn't. What happens is sometimes during the season, spring, you can have many particles out there. Any last question or comment? Can we maybe project that once again? Just wanted to see if they can explain this graph against density of energy. That one. Yes, that one without the map part of it, please. So what we have here on the x-axis is time, and on a y-axis we have periods and cycles. And colors is the variability. So the colors, as they become more red, that means that organisms are behaving or having more activity during those cycles. So this band of this 24-hour band or range, this is between 16 and 32 hours, so it's 24 hours here. We can see how energy was concentrated in this band per cycle. There are some red colors. So this tells us that these organisms in this moment where we saw the red bands, we can see that when that variability appears, is that the organism behaves or is having activity during the day. Then doing further analysis, we realize that these have patterns that have day and night. During the night they move the most. Since they move the most during the night, there's more probability that these can be detected. Then we have variability in the 12-hour range. So we have variability in the 12-hour range as well. So in the same way, something is happening. There's activity that changes every 12 hours as cycles, and it is affecting the organisms. While doing an analysis afterwards, we saw that this happens because of the tides. The tides change in Santa Elena Bay every 12 hours. So it goes up for every 6 hours for 25 minutes, and then it goes down for 6 hours during 25 minutes. This seems not to be the case all the time. So focusing on every 12-hour range, we're seeing that during this first 2 days, these are behaving and having activity with the tide, going into the mangrove when the tide goes up and coming out of the mangrove when it goes down. But during live tides, these are lost. So there is here around 4 or 5 days where it disappears. Energy, we would have to have that in the scale, the units. So yes, when it is live, tides energy is low. Any other question?
Bueno, gracias a todos y a todas por
All right, thank you everyone for listening to us.
Y bueno, espero que el mensaje
We hope that the message that we transmitted was as clear as possible of why it is important to use this type of equipment and tools. There are many others, but for biological studies as well, but the ones that are used the most are these ones here. So I think that we finish off for today. I just want to get a message out there if Maria del Milagro is out here. So please, she can go to see the organizers. That's just an announcement. Thank you. Have a good time.